Hi, my name is Alex, and this is my report for Lab 4. So the purpose of this lab was to examine Faraday's law through a magnet falling through a conducting pipe, in this case I just used a roll of aluminum foil, and then also to simulate the experiment and compare the simulated to the experimental values. And the findings were that the experimental average fall time was 0.2312 seconds, and the predicted fall time was 0.225 seconds. So these are some key concepts. First off, we have forces and Newton's laws of motion. For this lab, we need to know the force due to gravity because the magnet is falling, and also the magnetic force on a wire loop because the magnet creates a magnetic field that exerts a force on a ring of aluminum. And then we also need to know Newton's second law of motion, or the momentum principle, to update the position and velocity, and also Newton's third law of motion because the magnetic force exerted on the ring of aluminum by the magnet is equal and opposite to the magnetic force that the ring of aluminum exerts on the magnet. And then we also need to know Faraday's law, which states that a change in magnetic flux generates an nth, which is shown to the right with that equation. And Lenz's law states that nature abhors a change in flux, which is shown through the negative sign in Faraday's law. And it just means that an induced B field counteracts the original B field that created it. And we also need to know Ohm's law, which relates potential difference to current and resistance. So this is just a diagram showing the experiment. We have the system, which is a bar magnet, and the surroundings is the roll of aluminum foil and the earth. And in this case, the ring is just like a single slice of the roll of aluminum foil. So for this experiment, I measured the mass of the bar magnet and took measurements of the aluminum foil dimensions. And then I suspended the roll of aluminum foil in midair and dropped a magnet down through it, recording when it entered and exits the roll so that I could find the time between to see how fast it falls down the tube. So the data and results for this lab are that the average time was 0.2312 seconds. And so then for the computational model, I made the functions to calculate the magnetic field and magnetic flux. And then through a loop, calculated the magnitude of the gravitational force and the magnetic force on the magnet by basically through each ring of the aluminum foil. And then these were the results. So the predicted time was 0.225 seconds, which is smaller than the experimental value, which suggests that the dipole moment of the magnet should be larger, which was calculated back in lab 3 or lab 2. And then for the discussion questions, so the conclusion is that a magnet falls slower through a conductive tube due to the presence of a magnetic force that counteracts gravity. And some sources of error include incorrect value for the magnetic dipole moment from lab 2, and then contact or friction between the magnet and the tube, air resistance and measurement errors such as not getting the exact timing correct from the video, or also miscalculating the tube dimensions. So for the first what if question, if the resistivity of the conductor were reduced to as close to possible as to 0, the resistance would decrease to near 0 as well, which means that the induced current would increase and be very large, and that would also increase the magnetic field, and therefore the magnetic force of the tube on the magnet would increase, and therefore the forces would balance out more, so the magnet would fall more slowly and therefore increase the amount of time it takes for the magnet to fall. If holes or slots were cut into the tube, then that would disrupt the flow of current throughout the tube, and so the induced current would decrease, which would also decrease the magnetic field and the magnetic force. And because of that, the force due to gravity would be much larger relatively. So the magnet would fall faster and therefore decrease the time it takes for it to completely fall.